Good day, everyone. Today, we will talk about electrical power systems and how to improve their efficiency. First, I will give you an introduction to electrical power systems, and then I will give you an overview of electrical power systems. Later, we will talk about the types of electrical circuits, and then I will discuss electrical power production systems. I will also talk about estimating electrical load. I will then talk about electrical generators. We will then discuss on-site electrical power generation. We will also talk about direct current power systems. We will also talk about power distribution systems. And then I will talk to you about electrical power control. We will also discuss electrical power conversion or loads. I will also talk to you about power factor correction. And then I will discuss electrical motors. I will also talk to you about some products for energy conservation. And then we will go over an energy conservation checklist for electrical systems. So let's begin. So what are electrical power systems? Electrical power is used as an energy source for heating, cooling, ventilating, lighting, and other systems used in a building. When compared to all the other systems found in a building, electrical systems require less upkeep and maintenance. Electrical power is usually purchased from a local utility company. The cost of electrical power varies from one area to another. Many factors determine the rate paid for electrical power. These are the factors that affect the cost of electricity. The first factor is fuel prices. Fuel prices can vary greatly from one country to another. Even within a country, fuel prices can also vary from one area to another. Utility companies can sign long-term supply agreements with oil, gas, and coal companies to get favorable prices. The second factor is the cost of constructing power plants. The cost of constructing a power plant and operating it can vary greatly depending on the type of power plant a company wants to construct. On the next slide, we will compare the LCOE of different types of power plants. LCOE stands for Levelized Cost of Energy. It represents the average revenue per unit of electricity generated required to cover the costs of building and operating a generating plant during an assumed financial life and duty cycle. It can be computed by dividing the total life cost of a power plant by its total lifetime energy production. The second factor is the cost of transmission and distribution. Transmission and distribution lines cost a lot of money to build and operate. Their effect on electricity cost can depend on the distance between the power plant and the community or area that consumes the electricity. The fourth factor is weather conditions. Weather conditions can greatly affect the cost of electricity. They may also limit the types of power plants that can be constructed in certain areas. And the fifth factor is regulations. Regulations can also affect the cost of electricity. Some regulations may allow certain costs to be passed down to consumers. Other regulations can also provide subsidies or incentives for the construction of certain types of power plants, like wind farms and solar farms. These types of regulations may help lower electricity costs even just for a while. This is a comparison of the LCOE of different types of power plants. This table was obtained from the website of Stanford University, and it was prepared by Soumya Patapati and published on December 9, 2021. The highest LCOE is highlighted in red, and the lowest LCOE is highlighted in green. We will now talk more about electrical power systems. Electrical power production is an important part of the complete electrical power system. Electrical power must be distributed to the location where it will be used once it is produced. Electrical power distribution systems transfer electrical power from one location to another. Electrical power control systems are composed of devices that control electrical power. Electrical power conversion systems are also called loads. Loads convert electrical power into another form of energy, such as light, heat, or mechanical energy. Electrical power measurement systems make possible the control of electrical power. The following are the four fundamental units of electricity. The first unit is volt, the second is ampere, the third is ohm, and the fourth unit is watt. Figure 8.1 can show us the complete electrical power system. It starts with the electrical power production, and then electrical power distribution, and then the electrical power control, and then the electrical power conversion, and finally the electrical power measurement. What are the different types of electrical circuits? The following are the basic types of electrical circuits. We will define each in later slides. The first type is the resistive circuit. The second type is the inductive circuit, and the third type is the capacitive circuit. Most systems have some combination of each of these three types of circuits. A load is a part of a circuit that converts one type of energy into another type of energy. A resistive load converts electrical energy into heat energy. Resistive circuits are the simplest type of electrical circuit. The value of voltage can be obtained by multiplying the value of current by the value of resistance. Likewise, the value of current can be obtained by dividing the value of voltage by the value of resistance. The value of resistance can also be obtained by dividing the value of voltage by the value of current. The value of power can be obtained by multiplying the value of voltage by the value of current. This is an example of a resistive electrical circuit. A pure inductive circuit is a type of circuit in which the only quantity in the circuit is inductance, with no other components such as resistance or capacitance. The current in this type of circuit lags behind the voltage by 90 degrees. Inductance is a property of an electric circuit that slows down the rate of rise in the current. Inductance is a tendency of an electrical conductor to oppose a change in the circuit flowing through it. Inductance is caused by a counter-electromotive force that is produced when a magnetic force is developed around a coil of wire. The unit of measurement for inductance is Henry, or H. This is an example of an inductive electrical circuit. A pure capacitor circuit is a circuit that contains a pure capacitor which stores energy in the form of electricity. When two conductive materials, or plates, are separated by an insulating or dielectric material, the property of capacitance is exhibited. Capacitance is the ability of a system to store electric charge. The unit of measurement of capacitance is farad, or F. This is an example of a capacitive electrical circuit. Power relationships in AC circuits or alternating current circuits. An understanding of basic power relationships in AC circuits is very important when studying energy conservation. In resistive circuits, power is equal to the product of voltage and current, or P equals V times I. However, when a reactance, which is either inductive or capacitive, is present in an AC circuit, power is no longer a product of voltage and current. Since reactive circuits cause changes in the method used to compute power, there are a few methods used to express the basic power relationships in AC circuits. Apparent power, which is expressed in volt amperes or VA, or kilovolt amperes or kVA, is a product of voltage and current, or AP equals V times I. When using meters to measure power in an AC circuit, apparent power is the voltage reading multiplied by the current reading. The actual power that is converted to another form of energy by the circuit is measured with a wattmeter. The actual power is referred to as true power. Power factor, or PF, is the ratio of true power converted in a circuit to apparent power. PF is equal to true power, or P, divided by apparent power, or VA. Percent PF is equal to P over VA times 100. The maximum value of PF is 1, or 100%, which would be obtained in a purely resistive circuit. This is referred to as unity power factor. The phase angle between applied voltage and current flow in an AC circuit determines the power factor. This figure shows us the different power relationships. Apparent power is the hypotenuse, true power is the side adjacent to the phase angle, and reactive power is the side opposite the phase angle. There are two types of power that affect the power conversion in an AC circuit. The resistive part, which results in power conversion in the circuit, is called active power. Active power is called the true power of the circuit and is measured in watts, or W. The second part is that which results from an inductive or capacitive reactance and is plotted at a 90-degree angle with the active power. This power, which is called reactive power, does not produce an energy conversion in the circuit. Reactive power is measured in volt amperes reactive, or VAR. Let us now talk about electrical power production systems. Electrical energy must be supplied at the same time it is demanded by consumers. Accurate forecasting of load requirements at various times must be maintained by utility companies to predict the necessary power plant output for a particular time of the day, week, or year. The generating capacity of a power plant is subject to a continual change. Power plants may be idle when demand is low. The use of electrical power is forecasted to increase every 10 years at a rate that will cause a doubling of the kilowatt hours required. Some forecasts also show the rate of electrical power demand to have a leveling off period in the future. Conservation efforts and the saturation of the possible uses of electrical power for home appliances, industrial processes, and commercial use may support the idea that power demand will increase at a reduced rate in the future. So how do we estimate the electrical load? The total electrical load of a building consists of all equipment that use electrical energy. The amount of electrical energy used in a building depends on the type of electrical equipment connected to the system. These are the types of electrical loads. The first type is lighting systems. The second type is the HVAC systems, or the heating, ventilation, and air conditioning systems. The next type is small power systems supplied through convenience or plug-in outlets. The next type is water and sanitary systems. And the fifth type is miscellaneous load, which can include elevators, kitchen equipment, large electrical motors, and the like. It is necessary to analyze each type of electrical load attached to the electrical power system in order to conserve electrical energy used in a building. Programs to cut down on the load during peak operating periods can be initiated. The use of certain machines may be limited while other larger power-consuming machines are operating. Computers can be used to control load, especially in large industrial plants where it is very difficult to manually control the complex switching systems. To prepare computers for power consumption control, peak demand patterns of local industries and the surrounding region supplied by a specific power plant must be determined. The load of an industrial plant may then be balanced according to area demands with a power plant output. The computer may be programmed to act as a switch, allowing only those processes to operate which are within the load calculated for the plant for a specific period. If the load drawn by a company exceeds the limit, the computer can cause the system to increase power output to another part of the system. We will now talk about electrical generators. Generators used to produce electrical power require some form of mechanical energy input. This mechanical energy is used to move electrical conductors through a magnetic field inside the generator. A generator has a stationary part and a rotating part housed inside a machine assembly. The stator is a stationary part and the rotor is a rotating part. The generator has magnetic field poles of north and south polarities. The generator must have a method of producing a rotary motion or a prime mover connected to the generator shaft. A slip ring or brush assembly electrically connects the rotating conductors to an external circuit. The slip rings used on AC generators are made of copper. The slip rings are permanently mounted on the shaft of the generator. The two slip rings connect to the ends of the conductors. When a load is connected, a closed external circuit is made. Figure 8.6 can show us the basic parts of an electrical generator. Single-phase AC generators, or single-phase alternating current generators. In a single-phase AC generator, the armature conductors are connected in series to form a single circuit which generates a single-phase alternating electromagnetic force, or EMF. Single-phase generators are easy to produce and can be small and compact. A single-phase generator uses a single AC wave to create kilowatt outputs. Since these generators only work from one line of power produced between fewer conductive wires with up and down output cycles, Single-phase generators will not provide as steady a power source as their three-phase counterpart. As a single power line climbs to its peak and falls back down, so does the power level it produces. Single-phase generators don't wholly drop out or completely lose power, even at the lowest point. Low cycle currents typically remain unnoticeable unless this generator type runs over capacity. Figure 4.32 shows a stator core with a rectangular loop and two-pole rotor. Figure 4.33 shows the loop PQRS and field magnet in its initial position. The following are examples of single-phase alternating current or AC generators. Three-phase AC generators or three-phase alternating current generators. In the simplified construction of a three-phase AC generator, the armature core has 6 slots cut on its inner rim. Each slot is 60 degrees away from each other. 6 armature conductors are mounted in these slots. A three-phase generator has 3 currents that run in sequences simultaneously. These generators can produce robust and continuous power because the sequence currents always have one current near peak power. These currents require a strong voltage to provide constant power. Figure 4.35 shows the construction of a three-phase AC generator. Figure 4.36 shows the variation of EMFs or electromagnetic forces epsilon 1, epsilon 2, and epsilon 3 with time angle. The following are examples of three-phase alternating current or AC generators. This figure shows the differences between a single-phase AC generator and a three-phase AC generator. So, what is on-site electrical power generation? Let's talk more about it. On-site electrical power generation. High utility and fuel costs have caused several large industrial and commercial organizations to consider generating their own electrical power. Producing their own electricity provides a means for them to become independent from local utility companies. The initial investment required for electrical generating equipment can be large. This can be a deterrent for some companies if the cost savings cannot justify the large capital outlay. These are the factors to consider before choosing to do on-site electrical power generation. The first factor is the type of prime mover used, which can be a diesel or gas engine, a gas turbine, or a steam turbine. The next factor is the type of load that is served in the building. The third factor is the building occupancy schedule. The fourth factor is the possibility of equipment malfunction and projected maintenance costs. The next factor is initial installation costs. The sixth factor is the need for and availability of emergency backup power. The seventh factor is the possibility of cogeneration where process steam is used. Certain buildings could economically have their own system for generating electrical power. This makes the building independent of an electrical utility company. A major advantage of on-site power generation is that heat recovery systems may be used to supplement the operation of the generating systems. Steam or hot water from the heating system can be used for operating a turbine system which drives an on-site generator. Waste heat can be recovered to assist in the power generation process. The overall design of the HVAC system of a building and the possibility of supplementary heat recovery should be carefully analyzed to determine the effect on the total energy consumption of the building. Many buildings have a need for electrical power at all times. Emergency power generating systems or standby systems can be used when electrical energy for lighting and the operation of critical systems cannot be interrupted, like those at hospitals, security systems, and the like. We will now discuss direct current power systems. Alternating current, or AC, is used in greater quantities than direct current, or DC. However, many important operations are dependent on direct current, or DC. Electroplating and DC variable speed motor drives are two examples that show the need for DC power. DC power is used to start automobiles and portable equipment at home. The conversion of chemical energy into electrical power can be accomplished using electrochemical cells. Chemical cells can either be primary or secondary cells. Primary cells are ordinarily not usable after a certain period of time. After this period of time, their chemicals can no longer produce chemical energy. Secondary cells can be renewed after they are used by reactivating the chemical process that is used to produce electrical energy. This reaction is known as charging. Primary and secondary cells have many applications. When two or more cells are connected in series, they form a battery. When a load device, such as a lamp, is connected to a battery, an electrical current will flow through the cell. The current leaves the battery through the negative terminal. Then the current flows through the load device. Then the current re-enters the battery through the positive terminal. A complete circuit is established. This figure shows electric current flow through a battery circuit. Regardless of the type of primary cells used, its usable time is limited. When the chemicals are expended, the primary cell becomes useless. This disadvantage is overcome by secondary cells. The chemicals of a secondary cell may be reactivated by a charging process. Secondary cells are also called storage cells. Cells are devices that add electrical potential energy to charges moving through them. They do this using chemical reactions in the cell. There are two types of cells. The first type is a primary cell. The second type is a secondary cell. Primary cells are non-rechargeable. Once a cell gives up all its energy, the chemicals cannot react again. Examples of primary cells include zinc-carbon cells and any kind of cell that is non-rechargeable. Secondary cells are rechargeable. Once a cell gives up all its energy, the chemical reaction that causes it to lose energy can be reversed by a charger, giving it more energy to use in circuits. Examples include zinc-carbon cells and car batteries. These are some examples of the two types of batteries. This figure illustrates the differences between the two types of cells. This is another figure that illustrates the differences between the two types of cells. So what are power distribution systems? Power distribution systems. Power distribution systems are an important part of electrical systems. To transfer electrical power from a source to the place where it will be used, some type of distribution network must be utilized. The distribution of electrical power involves a very complex system of interconnected power transmission lines. Power transmission and distribution systems are used to interconnect electrical power from the generating station to its point of utilization. An important part of power distribution systems is an electrical device known as a transformer. Transformers control massive amounts of power for more efficient distribution. A transformer is a passive component that transfers electrical energy from electrical circuit to another circuit or multiple circuits. Transformers provide a means of converting and alternating current voltage from one value to another. If an AC current that is constantly changing in value flows in the primary winding of a transformer, the magnetic field produced around the primary winding will be transferred to the secondary winding. An induced voltage is developed across the secondary winding of the transformer. In this way, electrical energy can be transferred from the source, which is the primary winding circuit, to the load, which is the secondary winding circuit. This figure shows the pictorial drawing of a transformer. This figure shows a schematic symbol for a transformer. The efficiency of a transformer can be computed by dividing the power output by the power input and multiplying that by 100. Transformers are classified as step-up or step-down transformers. The step-up transformer has fewer turns of the wire on the primary than on the secondary. If the primary winding has 100 turns and the secondary winding has 1000 turns, a turns ratio of 1 to 10 is developed. If 10 volts AC is applied to the primary from the source, 10 times that voltage, or 100 volts AC, will be transferred to the secondary circuit. A step-down transformer has more turns of wire on the primary than on the secondary. If the primary winding has 500 turns, while the secondary has 50 turns, or a 10-to-1 ratio, and 120 volts AC is applied to the primary from the source, then 1/10 that amount, or 12 volts AC, will be transferred to the secondary circuit. This figure shows the two types of transformers. The first one, the one on the left, is a step-up transformer, and the second one, the one on the right, is a step-down transformer. Conductors are used to transfer electrical current from one location to another. The unit of measurement for conductors is a circular mil, or C-mil, since most conductors are round. 1 mil is equal to 0.001 inch. The cross-sectional area of a conductor in circular mils is equal to the square of its diameter, or d squared. If the conductor is not round in shape, its area may be found using this formula. Area, which is in C-mil, is equal to area, which is in square mils, divided by 0.7854. The resistance of a conductor expresses the amount of opposition it will offer to the flow of electrical current. The unit of measurement for resistance is the ohm. Resistance is equal to resistance times length in feet divided by the square of the diameter. This table summarizes the resistivity of some common conductors, which include silver, copper, aluminum, and tungsten. Ampacity is the measure of the ability of a conductor to carry electrical current. All metal materials will conduct electrical current to some extent. Copper and aluminum are the two most widely used metal materials. Insulation is used to cover materials to stop heat or electricity from escaping. It offers a barrier to the progression or transmission of any form of energy through the insulated surfaces. Synthetic insulation for electrical wire and cable is classified into two broad categories: thermosetting and thermoplastic. Thermosetting insulation has a higher tolerance to higher temperatures compared to thermoplastic insulation. Thermoplastic insulators have a high risk of heat deformation at inappropriately hot temperatures. Thermosetting insulation has superior flexibility, which it can retain in cold temperatures. There are many devices that are used to protect electrical power systems from damage. These devices include switches, fuses, circuit breakers, lighting arresters, and protective relays. Some of these devices automatically disconnect electrical equipment before any damage can occur. Other devices sense changes from the normal operation of equipment and make the changes necessary to compensate for abnormal circuit conditions. The most common electrical problem that requires protection is the short circuit. The purpose of any type of protective device is to cause a current-carrying conductor to become inoperative when an excessive amount of current flows through it. The simplest type of protective device is a fuse. A fuse is an electrical safety device that operates to provide overcurrent protection of an electrical circuit. Its essential component is a metal wire or strip that melts when too much current flows through it, thereby stopping or interrupting the current. Circuit breakers are somewhat more sophisticated overload devices than fuses. Although their function is the same as that of fuses, circuit breakers are much more versatile. In three-phase systems, circuit breakers can open all three hot lines when an overload occurs. Circuit breakers may also be activated by remote control relays. Relay systems may cause circuit breakers to open due to changes in frequency, voltage, current, or other circuit variables. Circuit breakers are designed so that they will automatically open when a circuit occurs which exceeds the rating of the breaker. Circuit breakers must be reset manually. Most circuit breakers employ either a thermal tripping element or a magnetic trip element. Power distribution inside buildings. Electrical power is delivered to the location where it is to be used, and then it is distributed within a building by the power distribution system. Various types of circuit breakers and switchgear are employed for power distribution. Feeder lines and branch circuits. The conductors that carry current to the electrical load devices in a building are called feeders and branch circuits. Feeder lines supply power to branches that are connected to them. Primary feeder lines may be either overhead or underground. Overhead lines are usually preferred because they permit flexibility for future expansion. Underground systems cost more, but they are much more attractive in appearance. Secondary feeder lines are connected to the primary feeder line and supply power to individual sections within the building. The electrical service entrance. Electrical power is brought from the overhead power lines or from the underground cable into a building by what is called an electrical service entrance. The type of equipment used for a service entrance may include high current conductors and insulators, disconnect switches, and protective equipment for each load circuit. The three-phase power system. Since industrial and commercial buildings generally use three-phase power, they rely upon three-phase distribution systems to supply this power. Large three-phase distribution transformers are usually located at substations adjoining the industrial plants or commercial buildings. Grounding of distribution systems. Distribution systems must be grounded at substations and at the end of the power lines before the power is delivered to the load. Grounding is necessary at substations for the safety of the public and the power company's maintenance personnel. Ground fault protection. Ground fault interrupters, or GFIs, are now used extensively in industrial, commercial, and residential power distribution systems. These devices are designed to eliminate electrical shock hazards resulting from individuals coming in contact with a hot AC line or a line-to-ground short. Wiring design. The wiring design of electrical power systems can be very complex. There are many factors that must be considered when wiring a building. When buildings are constructed or renovated, they are inspected to see if the electrical wiring meets the standards of the local ordinances. Voltage drop. Although the resistance of electrical conductors is very low, a long length of wire could cause a substantial voltage drop or reduction of voltage to the load. A voltage drop is current times resistance, or I times R in the current. Whenever current flows through a circuit, a voltage drop is created. Ideally, the voltage drop caused by the resistance of a conductor will be very small. However, a longer section of electrical conductor has a higher resistance. Branch circuits. A branch circuit is defined as a circuit that extends from the last overcurrent protective device of the power system. Branch circuits are 15, 20, 30, 40, or 50 amperes in capacity. Loads larger than 50 amperes would not be connected to a branch circuit. The maximum rating of an individual load is 80% of the branch circuit current rating. A 20 ampere circuit could not have a single load which draws more than 16 amperes. Branch circuits must be designed so that sufficient voltage is supplied to all parts of the circuit. This figure shows a single-phase power distribution panel. Feeder circuits. Feeder circuits are used to distribute electrical power to power distribution panels. Many feeder circuits extend for very long distance. Therefore, the voltage drop must also be considered in feeder circuit design. The amount of current that a feeder circuit must be designed to carry depends on the actual load demanded by the branch circuit power distribution panels which it supplies. Each feeder circuit must have its own overload protection. What is electrical power control? Electrical power control. The control of electrical power systems is very important. Control is the most complex part of the electrical power system. Control equipment and devices are used in conjunction with many types of electrical loads, such as motors, lighting, and heating systems. Let's now discuss electrical power conversion, or loads. Electrical power conversion, or loads. Electrical load devices that are used in buildings are very important parts of electrical power systems. The load of any system performs a function that involves power conversion. An electrical load converts electrical energy to some other form of energy, such as heat, light, or mechanical energy. Electrical loads are usually classified according to the function they perform, which can be lighting, heating, and mechanical. Load characteristics. To plan for power system load requirements, it is necessary to understand the electrical characteristics of all the loads connected to the power system. The types of power supplies and distribution systems that a building uses are determined by the load characteristics. One primary factor that affects the electrical power system is the presence of inductive loads, which are mainly electric motors. To counteract the inductive effects, utility companies use capacitors to correct the power factor as part of the system design. The inductive effect increases the cost of a power system and reduces the actual amount of power that is converted to another form of energy. Demand factor. One electrical load relationship that is important to understand is the demand factor. The demand factor expresses the ratio between the average power requirement of a building and the peak power requirement. The demand factor is equal to AD divided by PD, where AD is the average demand and PD is the peak demand. So, what is power factor correction? Let's talk more about it. Power factor correction. Most industries use many electric motors. The power system operates a power factor of less than unity or less than 1. It is undesirable for an industry to operate at a low power factor, since the electrical power system will have to be able to supply more power to the industry that is actually used. The value of power factor decreases as the reactive power or unused power drawn by the industry increases. As reactive power is increased, more volt amperes must be drawn from the power source. An increase in reactive power causes a decrease in the power factor. Power factor, or PF, is equal to true power in watts divided by apparent power in volt amperes. As VA increases, the value of PF will decrease. The effect of the increased capacitive reactive power in the system is to increase or correct the power factor and thus reduce the current drawn from the power distribution lines that supply the loads. Power factor problems are usually not encountered in residential or commercial buildings because they do not use as many electric motors as industrial buildings. We will now discuss electrical motors. Electric motors are a very important type of electrical load. Motors convert electrical energy into mechanical energy. To produce a rotary motion, a motor must have an electrical power input. This figure shows the basic parts of a DC motor, or a direct current motor. The rotating effect of a motor is produced by the interaction of two magnetic fields and is called torque. The torque produced by a motor depends on the strength of the main magnetic field and the amount of current flowing through the rotor conductors. Direct current or DC motors. DC motors are motors that operate from direct current power sources. DC motors are used when speed control is desirable. DC motors are classified as series, shunt, or compound wound machines depending on the method of wiring, the armature and field windings. Horsepower rating. The horsepower rating of a motor is based on the amount of torque or rotary motion produced at a motor's rated full load. Horsepower, which is the usual method of rating motors, can be expressed mathematically as HP is equal to speed times torque divided by 5,252. HP can also be equal to 2 pi times speed times torque divided by 33,000. HP can also be equal to speed times torque divided by 5,252, where HP is the horsepower rating and 2 pi is a constant equal to 6.28. Universal motors. Universal motors may be powered by either AC or DC power sources. The universal motor is designed so that it will operate with either AC or DC applied. Universal motors are used mainly for portable tools and small motor-driven equipment. AC induction motors. A popular type of single-phase AC motor operates on what is called the induction principle. Induction motors have a solid rotor, which is referred to as a squirrel cage rotor. This type of rotor has large diameter copper inductors that are soldered at each end to a particular connecting plate. Speed of AC induction motors. Speed is equal to frequency times 120 divided by the number of stator poles, where speed is in RPM, frequency is in Hertz, and the number of stator poles is the number of windings. This figure shows a single-phase AC induction motor. Other types of electrical motors include: number 1, split-phase induction motors. Number 2, capacitor motors. Number 3, shaded pole induction motors. Number 4, single-phase synchronous motors. Number 5, three-phase induction motors. Number 6, three-phase synchronous motors. Number 7, wound rotor induction motor. This figure shows the construction of the split-phase motor. This figure shows a split-phase motor. This figure shows a single-phase motor connection with two capacitors. This figure shows a shaded pole induction motor. This figure also shows a shaded pole induction motor. This figure shows the difference between slip ring and squirrel cage induction motors. Selecting electric motors. The following considerations have to be made when selecting electric motors. Number 1, the source voltage and power available. Number 2, the effect of the power factor and efficiency of the motor on the overall system. Number 3, the effect of the starting current of the motor on the system. Number 4, the type of mechanical load. And number 5, the expected maintenance it will require. The efficiency of an electric motor is equal to power output divided by power input times 100, where P in is equal to the power input in horsepower and P out is equal to the power output in watts. PF, or power factor, is equal to true power in watts divided by apparent power in volt amperes, where PF is the power factor of the circuit, P is true power in watts, and VA is apparent power in volt amperes. What are some of the products for energy conservation? Let's talk about some of them. Products for energy conservation. Many electrical products have been developed recently with the purpose of energy conservation in mind. One of these products is the energy-efficient motor. The manufacturers and users of electric motors are becoming more concerned about motor efficiency. Motors consume more energy than any other type of electrical load. Another product for energy conservation is the variable speed motor controller. Some types of motor-driven equipment operate more economically when a variable speed controller is used. Varying the speed of such equipment as fans and pumps can reduce their overall energy consumption. This is an example of a variable speed motor controller. Another product for energy conservation is the automatic cut-off timer. Many types of electrical equipment waste energy because they are allowed to operate when they are not actually needed. This is an example of an automatic cut-off timer. Another product for energy conservation is a single-phase to three-phase converter. Three-phase motors are generally more efficient than single-phase motors. It is advisable and desirable to use three-phase motors in as many applications as possible. This is an example of a single-phase to three-phase converter. Another product for energy conservation is the demand monitor. The demand charges imposed by utility companies can often represent a significant portion of an electricity bill. A reduction in peak electrical demand can reduce the demand charge paid by a business. Peak demand of electricity is reduced by staggering the startup or operating time of large equipment. This is sometimes called load shedding. Electrical demand may be monitored by using a demand control relay alarm, which sounds when a predetermined amount of electricity is being used. The following are examples of demand monitors. Let us now go over an energy conservation checklist for electrical systems. This is the first part of the energy conservation checklist for electrical systems. We can check for the following items and apply the respective corrective action for each item. This is the second part of the energy conservation checklist for electrical systems. We can do the same thing we did with the first part. We can first check the following items and apply the appropriate corrective action for each item. This is the third and final part of the energy conservation checklist for electrical systems. We can start by checking the following items and then applying the appropriate corrective action for each item. The following references were used to prepare this report. Reference number 1. Reference number 2. Reference number 3. Reference number 4. And reference number 5. Thank you very much, everyone, for listening to my report. I hope you enjoyed it.